Have you ever been wrongly accused of stealing the last of the office milk? What if somebody said that they could scan your brain and prove that you were guilty? Now you'd feel sure that that scan could prove that you were innocent instead, wouldn't you? But only if you knew that the brain scanning used was accurate. In America, companies are already trying to use brain scanners as lie detectors. One such company is called No Lie fMRI. And they use brain scans called fMRI in order to try and provide them as evidence in courts of law. Not for minor petty milk theft, but for serious crimes such as rape and murder. The problem with this is that fMRI scans are far from error-proof. Recently, a team put a dead Atlantic salmon into a brain scanner. Surprisingly, they found brain activation. Now that seems a little fishy to me. In the case of the salmon, they found activation because the proper statistical corrections were not made afterwards. However, there are many reasons why fMRI scans may not be wholly accurate. My PhD research overall aims to improve the accuracy of these brain scans. And how I'm going to do that, I have to tell you a little bit more about how fMRI works. Now, fMRI does not directly scan your brain cells. Instead, it measures the changes in the blood in your brain. Now, the blood in our brain carries around oxygen, which is used heavily by our brain cells. So if there's more oxygen, our brain cells are working harder, we think. But these fMRI scans never actually directly scan those brain cells. You can imagine how difficult that makes it for them to be accurate. It's a little bit like trying to count monkeys at the zoo by looking at all the empty banana skins that are down on the floor. Now, I'm very lucky in that by using different techniques, I can see the blood in the brain and the changes, and also the changes in the brain cells in the brain. So I can see the monkeys and the bananas. Now, hidden within these brain cell signals, there are characteristic brain signal shapes, like this one. And I know that these cause a distinct change in the blood, like this, because I can see both the brain cells and the blood in the brain. And now I can take this knowledge back to my fMRI scan, which only looks at the blood in the brain. And I can look for this distinct change in the blood in the brain in the fMRI scan. And when I find it, I know that it's caused by a characteristic brain signal like this. It's a little bit like if somebody gave you a coded message and told you what one of the symbols meant. You'd be one step closer to accurately understanding the whole message. And I hope that my research can help us to accurately understand what fMRI can tell us about the brain's messages.